Welcome to This Explainer. Today, we're doing something really cool. We're treating this like a masterclass. Think of it as a highly practical, zero-filler short course on the history of engineering. If you've ever wondered how humanity went from dragging rocks in the mud to building massive skyscrapers and nuclear power plants, well, you are in the exact right place. We're going to strip away all the complex jargon and look at the absolute foundational concepts that actually built our modern world. So get ready to take some mental notes because every single thing we cover today is a high-yield, crucial concept.
Okay, let's dive right into our syllabus. We'll start with the dawn of practical tools, move into a Roman infrastructure masterclass, and then analyze the industrial power shift. After that, we hit the most critical part, comparing theory versus applied execution to see what truly drives progress. And finally, we'll wrap up with your top 3 key takeaways. Let's get started.
Section 1. Dawn of Practical Tools, Building from the Ground Up.
To really grasp engineering, we've got to look at the very first tech startups in human history. Long before anyone had complex math or physics degrees, humans relied on fundamental mechanical principles to create things that just worked. I want you to imagine seeing this concept for the literal first time, the wheeled cart. Originating over by the Tigris and Euphrates rivers with the Mesopotamians, this was essentially version 1.0 of the startup world. Before this, our capacity was limited strictly to what we could carry on our own backs or drag on a heavy sled. The wheeled cart fundamentally changed human mechanical leverage forever. It wasn't about complex theory, It was a simple, elegant solution to the very real problem of moving heavy things over long distances.
And this right here brilliantly illustrates exactly what we're talking about. I mean, it's not just a piece of wood, it's a profound leap in physical reality. By placing an axle through a circular frame, ancient engineers slashed friction and multiplied their labor force exponentially. This specific mechanical principle, the wheel and axle, is literally the bedrock of almost every moving machine we still use today. But here's the thing, early engineering wasn't just about moving dirt and rocks, it was about understanding the world around us. Enter the astrolabe. If the wheeled cart was history's first cargo truck, the astrolabe was the ancient world's GPS. It was an angle measuring device built for pure, practical astronomical observation and navigation.
Just look at the intricate execution here. The Mesopotamians weren't just slapping crude tools together, they were crafting precise, calibrated instruments. Using this, ancient navigators and surveyors could determine their latitude, tell time, and make the specific measurements that were absolutely crucial for expanding their empires and trade routes. It was essentially hardware built to decode the software of the night sky.
Now let's blitz through a quick timeline of high-yield historical milestones. By 200 BC, the Egyptians are using rope surveying to build the monumental pyramids. Jump to 600 BC, and the Greeks are constructing the massive Pharos of Alexandria lighthouse, along with 3,300-foot-long tunnels. But honestly, the most highly testable concept on this timeline goes all the way back to the Mesopotamians, the Code of Hammurabi. Why does that matter? Because it represents the literal birth of professional responsibility and quality assurance. It sent a crystal-clear message: if your building falls down, you are held accountable. That was the exact moment engineering became a true regulated profession.
Section 2. Roman Infrastructure Masterclass, Scaling Up.
This is the era where the focus of engineering dramatically shifted. We evolved from building single, standalone tools to designing massive, permanent societal infrastructure. The Romans didn't just build things, they engineered entire societies. And their secret weapon? Hydraulic cement. I want you to think of hydraulic cement as the source code of the Roman Empire. Before this, you basically stacked rocks and just hoped they stayed put. But with hydraulic cement, Romans created a revolutionary binding material that allowed for massive, durable construction that actually hardened underwater. It unlocked an entirely new, awe-inspiring scale of building.
Just look at these highly tested, practical applications. They scaled up absolutely everything. They built massive construction machines using pile drivers and giant treadmill hoists. They built the Appian Way, the first major paved road network, which completely revolutionized logistics. They engineered the Colosseum, a massive elliptical amphitheater that still stands today as a total architectural marvel. But their absolute crowning achievement in public works? The aqueduct, starting with the Aqua Appia.
So the crucial point to remember here is this. These aqueducts weren't just pretty stone arches. No way. They were the ultimate practical solution to a critical human survival problem, delivering a clean, public water supply to massive, rapidly growing urban populations. They pulled this off relying on incredibly precise gradients and gravity stretching over miles of terrain.
The Romans proved that engineering wasn't just about making things, it was about sustaining human civilization at scale.
Section 3. The Industrial Power Shift, the Machine Age.
Fast forward through the Middle Ages, where we saw some really great innovations, like gunpowder and windmills from Islamic and Chinese civilizations, and boom, we arrive at the 1700s. Now, what's really interesting about this is the sheer visual contrast. On one side, we have the absolute pinnacle of ancient labor, a Roman treadmill hoist powered entirely by human sweat and muscle. On the other side, we see the massive mechanized leap of the Industrial Revolution, where human and animal muscle was violently and permanently replaced by mechanical and chemical power. We stopped relying on what we could lift ourselves and started harnessing the invisible elements of the earth to do the lifting for us.
The bedrock of this entirely new era was steam power. And getting down to first principles, it wasn't invented just for the sake of cool science. It was a highly practical solution to a massive industrial headache: pumping water out of flooded coal mines in the 1700s. By using the principle of water vapor condensation to create a vacuum, engineers figured out how to drain these mines, which then fueled the rest of the Industrial Revolution. Talk about necessity being the mother of invention, right?
From there, the refinement of practical problem-solving just went into absolute overdrive. William Gilbert coined the term electricity in the 1600s and linked it to magnetism. In 1783, John McAdam revolutionized road construction by using crushed stone and gravel, literally paving the way for modern transport. And later on, Henry Ford introduced modern mass production, making automobiles affordable for the average person. The thread connecting all of these milestones is that modern engineering is just a relentless, continuous refinement of practical execution.
Section 4. Theory versus applied execution, the ultimate comparison.
All right, now that we've seen how engineering evolved over thousands of years, we really need to compare the two fundamentally different approaches to the discipline that are outlined in our source text. This is the climax of our masterclass right here. On one side, we have traditional, theoretical engineering. This is your scientific, theoretical, and conceptual design. It's heavily reliant on mathematics and economic knowledge to investigate and innovate at a high conceptual level. On the flip side, we have engineering technology. This approach is entirely focused on application, execution, and manufacturing solutions. It's about taking the blueprint, putting on the hard hat, and actually building the structure, the instrument, or the system in the real physical world.
So, which approach is actually best? Well, based on everything we've reviewed from the history of human progress, here is the verdict. Engineering technology, meaning applied execution, is the ultimate, most impactful approach. Why? Because theory is wonderful, but theory alone doesn't pump water out of a flooded mine. Theory doesn't build a Roman aqueduct that stands for 2,000 years. Applied execution is what directly manufactures the real world. Without the hands-on execution of engineering technology, all the brilliant scientific theory in the world just stays on paper.
Section 5. Top 3 key takeaways. Your final review. Let's move to and see how this builds into our final exam review. I want you to lock these core concepts in, so if you are ever tested on the history of engineering, you've got the exact answers ready to go. Number 1. Ancient, basic tools like the wheel and the astrolabe weren't primitive at all. They created the fundamental mechanical foundation we still rely on today. Number 2. The Romans changed the game by scaling engineering from individual tools into massive, permanent societal infrastructure, largely thanks to the magic of hydraulic cement. And number 3, while theoretical engineering maps the route, applied execution, engineering technology, is the ultimate driver that actually builds human progress.
Which leaves us with this final thought. You've just seen a crash course in how we engineered our way from dragging carts in the mud to mass-producing automobiles. If applied execution built the entire past that surrounds you, how will the next era of engineering shape your future world? Keep your eyes open because the next massive shift in applied execution is happening all around you right now. Thanks so much for joining me for this explainer.